let's start. So first, I created some extra exercises for you to practice the algorithms we are learning for the theoretical topics. For example, how to convert tables into normal forms, or how to check the serializability of transaction schedules, which will be learned today. So I will keep updating this exercise, and please stay updated. And if you want more exercises, because the original algorithm in the slides, in our lecture slides, is made up of pseudocode and some mathematical symbols, and I think it could be hard for some of you to understand. So instead of reciting those algorithms, you should comprehend them, and you should understand how they work. So that's why I decided to create more step-by-step exercises for you to really understand them. And that's the first thing. And now let's come to today's lecture. So this is our outline today. So we will go through some announcements, and we will have a quick recap of what we have learned in our last lecture. And then we will learn 3 topics today. The first one is following our previous lecture about how to do performance tuning. And the second one is about transactions. And the last one is about this serializability of transaction schedules. So the first announcement is that there's no quiz this week, but next week we will have quiz. The last quiz. And the second announcement is about assignment 2. For assignment 2, we have released 3 questions for now, and we have decided to reduce the scope. So in the end, you will have 4 questions in total to practice with, and we will extend the due date by 3 days. So it's the Monday of week 11. And although we are not releasing the questions all at once, you are actually given a lot of time per question on average. So I hope you can really work on them well. And as I said, you should submit if you have special considerations, you should submit them to the portal earlier. And you should submit your ELP extension request 24 hours before the due date. And now let's come to the recap. So in our last lecture, we learned about relational algebra. And do you still remember the definition of relational algebra? So what is that? Is actually the formal form of the database operations, and it could be think of as what is exactly executed by the DBMS. So that's the definition or the concept of relational algebra. And we learned several operations for relational algebra. We learned rename, we learned selection, and we learned projection. So can you still remember the difference between selection and projection? Selection is used to select what? To extract what kind of information? Yes. Yes. Actually, projection, although the name of selection sounds like select in SQL queries, it is not used. It is not used the same as in SQL. It's used only to extract information from tuples, and projection is used to extract column values or the attributes. And we have also learned some set operators used for relational algebra, and they are essentially the same as SQL, the mechanism. And we also learned several product and joins for relational algebra. And the second topic we learned in our last lecture is about query execution. So for query execution, we learned that there could be a mapping between SQL and relational algebra. So you should be able to do this mapping. And we also learned that DBMS will use this execution plan of relational algebra operations to estimate the cost of a particular query. So that's what we learned. And in next week, we will have a summary of the entire course. So this course, today's lecture, is the last lecture that we will be to learn new knowledge. So that's all about the recap. And now let's learn something new. The first topic today is performance tuning. So in our last lecture, we ended at the point where we know that DBMS can estimate the cost of queries using the execution plan made up of operations of relational algebra. But from the developer point of view, how can we utilize this information to optimize our queries? So that's the question, and this is what we are going to learn here. So in order to make the DB applications efficient, to optimize the efficiency to the execution time, it is useful to know what operations on the data that the application require. So it's useful to know what kind of operations we need. And the second one is because there are different alternatives for implementing the same mechanism of data retrieval. We need to know how much each implementation will cost. And then, as a developer, we should encourage the DBMS to use the most efficient methods. We cannot directly manipulate how these DBMS work, but we can somehow encourage it to work in an efficient way. And this could be achieved by using indexes and avoiding some bad practices. So that's what we are going to, that's how we boost the performance. And the choices of application programmers could affect query costs. And the first one is how the queries are expressed could affect the performance of the query, could affect the execution time. And here are some general tips. So generally, join is faster than subquery. So this is generally, join is faster, especially if subqueries are correlated. So correlated subquery means that the subquery, inside the subquery, we are referring to the variables of the parent query. So this is called correlated subquery. So if correlated subquery could be very slow, and we will show you some examples later. And another good practice is to filter first and then join, because if you train up joins, you could end up with a very large intermediate table. So remember, in our last lecture, we learned the Cartesian product. So Cartesian product will give us a very large table. and it is the same for most of the outer joins. So it will give us a very large table if we train up multiple joins, and this could slow down the overall the execution. And the last one here is we should avoid applying functions in the conditions of where or group by, because those conditions will be checked against array tuple, and we don't want to execute a function for array tuple of the for array tuple of a table. So that's why we should avoid this. And the second practice here is we should consider creating indexes for tables. So indexes for tables are actually similar to indexes for articles. So index can speed up the filtering based on the indexes, the indexed attributes, and but we need to tell the database, DBMS, which attributes should be indexed, and we will learn that later. And indexes generally are only effective for equality greater than or less than, so it's mostly useful for numeric values, and it is useful if we are doing filtering more frequently than doing updating. So if we are updating the table a lot, index may not help us. But if we are filtering the data according to the indexed data or attributes, it could speed up the overall execution. And so as you can see, there are two main factors, two main choices that could affect the cost. The first one is how the queries are expressed. The second one is about indexes. And now let's learn them one by one. And how queries are expressed could affect the performance of database. So from the programmer's point of view, the query we can't modify, or we can't directly ask the DBMS query optimizer to behave in a particular manner. So it will always try to optimize our queries, but some of the patterns inside the query could prevent the optimizer from optimizing our query. So that's what we should avoid. And we as I said, we have no control over the optimization process. It is totally controlled by the DBMS. And what we could only do is to avoid limiting the query optimizer. So here's an example of how why the choice of how queries are expressed could affect the performance. So let's consider this example here. So in this example, we would like to have a query to find salespeople earning more than 50K. So this is one of the possible queries we could have. So we can have a subquery here. We can select the name from the employee table, and then for the condition to filter to get what we want, we can set the constraint for the salary to be larger than 50K, and we should make sure that the employee is a salesman. So we should say that, okay, the employee ID should be from the intermediate table of the salespersons. So this is how we can do it. As you can see here, this is a subquery, and it is not correlated because it is not referring to the variables of the outer query. So it's not correlated, it's just a subquery. And a query evaluator of the DBMS may use this strategy to retrieve us the data. So what it will do is it could execute the sub query first to give us an intermediate table of sales employees. And for each employee, it will check two conditions: whether this person is in the sales table, in the intermediate table, and whether the salary of this employee is larger than 50K. So this is how the DBMS will interpret this query. And this is not a good query because as you can see here, it is very likely that the DBMS will loop through all the employees, and even if the employee is not in sales, because we are selecting from the employee table here, so it will essentially make the DBMS to loop through the entire employee table, and this is not efficient. And plus, we are doing a condition with two checks here, so this is also not very efficient. So in general, this is not a good query. And there's a different expression for implementing the same query. So what we can do is we can join two tables together. We can select the name from the employee table and join it according to the employee ID. And we set the condition to be the salary is larger than 50K. There's a typo here. And the department is sales. And in this case, the evaluator may choose to execute the query like this. So it will generate an intermediate table according to the department, and then it will join the table of the employee with the intermediate table, as indicated by the join keyword here in the original query. And then it will loop through this newly joined table and look for the employees whose salary are larger than 50K. So in this case, this one is a better query because in this big loop here, we are only examining the sales employees. We are not examining the entire table of employees. And this if condition here is simpler. So that's why this join is a better choice here. And let's see a last example of correlated subquery. So correlated subquery, as we just mentioned, it refers to the values from the outer query. So in this case, we can also implement the query with a correlated subquery. This subquery is correlated because it's referring to this variable E here of the outer query. And let's see why correlated subqueries are not efficient. Because as you can see here, the DBMS will likely to use this strategy to retrieve the data. So first it will go through the table of employees, because we are selecting from the employee table here. So it will loop through the entire table of employee, and then for each, because we are using this variable E here, for each we need this, we can't, in this case, because remember in our previous example, the evaluator is executing the subquery first because it's not depending on the value of the outer query, But here we have to run the query, the subquery later, because it depends on the variable of the auto query. So in this case, we have to run a query for each of the employee here. And this is very, very bad actually, because previously we need to run 1 or 2 queries, and now we are running a lot of queries, and this could slow down the execution speed a lot. So that's why correlated queries are bad. And just now we mentioned that apart from how we express the query, the using indexes could also affect the performance of the execution. So indexes actually provide efficient content-based access to tuples, and we can build indexes on any combinations of attributes. So this is the syntax for defining indexes in Postgres, and this is a very basic syntax here. You can actually add a lot more options. So the first thing about this, the thing to take note here is the attribute here could be the name of an attribute, or it could be any arbitrary expression. And create index also allows us to specify whether this index is created for unique values. And we can also specify the access method for retrieving the data for the index. For example, we can choose to use binary tree. We can also use hash tables. And you can refer to the official documentation of Postgres for all the possible options here. Indexes can significantly improve query costs. But here are some considerations when you use indexes. So the first thing to consider is whether the indexed attribute is frequently used in, or it is involved in some expensive queries. If not, we'd better not index that attribute, because it will incur some cost when we update the data. So that's the first thing we need to consider. The second thing here is, should we create an index on a collection of attributes? And because we need to decide the collection of attributes we want to use. And the third one here is the table containing the attribute frequently updated? So if so, we should be careful, because index will slow down updates sometimes. So that's why it's not always good. And the last one is when we do because we can specify how the DBMS will retrieve the indexed data, or how the DBMS will look for the indexed data. So we can specify the algorithm here. And if the attribute we are indexing is involved in equality tests, it's better to use hash table to search for that index. And if the attribute is involved in range tests, it's better to use binary search tree here for looking into the indexed data. And now we know that, okay, we can the choices of how we express queries and how we build up indexes could affect the performance. But how can we do the tuning of the queries to make it more efficient? So sometimes a query can be rephrased to affect the performance, and by doing two things. So the first one is, of course, to avoid those unnecessary or very expensive operations, like the unnecessary queries introduced by correlated subqueries, or it could actually help the optimizer to make use of the indexes. So we can encourage the DBMS to use indexes. And here are some examples. Here are some bad examples actually, which may prevent optimizers from using indexes. So the first one is, if we just index the attribute of salary, if we just index the salary attribute, and we use it for calculation here in the condition, then it is not, the index is not used. So this is the first counterexample. And the second and third are checking string patterns is not using the index, and checking against null value is also not using index. So, but these two are somehow hard to fix, and maybe we just don't fix them in practice. And the last one here is sometimes if we use subqueries, then indexes are not used. But we can always fix this by changing it into some conditions. And that's from the usage of index point of view. There are some other tricks for query tuning which could also affect the performance. So the first one is most of the time, if we want to select distinct, it requires a sort of the table values, and we should think about, is the distinct here really necessary, or at this stage of the query, or can we do it later? So this is one thing, because if we sort on a smaller table, a smaller set of data, then it could be much faster. So this is the first trick. And the second one is, if we have multiple drawing conditions available, we should draw in the attributes that are indexed. So for example, normally we could index the primary key or the ID of a piece of data, and normally we don't index strings. So we should join table according to the indexed data or the IDs, and avoid joining on strings, because it's not only because the index could speed up the overall performance, it's also because string comparison is quite costly. So if we have choice, we should avoid running on strings. And the last tip here is, sometimes the OR operator prevents the index from being used. So we can replace the OR condition here by a union of non-OR clauses. So if we want to select a condition made up of an OR operator here, we can actually select them separately and then union the results. So this is how we can tune our queries. And there's apart from the strategies of tuning our queries, there's actually a very useful tool or utility provided by Postgres to help us to analyze the performance of our queries. So actually Postgres provides the explain statement to give us a representation of the query execution plan, and it can also give us the information of the actual cost of those execution plans. And the usage of this this statement is like this. So we just explain, and optionally we can put the keyword analyze here, followed by the query we would like to analyze. So without, actually, as you can see here, the analyze keyword is optional. So without analyze, this explain statement will estimate the cost without executing the query. With analyze, the explain statement will execute the query and print out the real cost, the time cost for this query. But do note that if we use the analyze keyword here, the execution time could be different every time because of multiple reasons, because of the hardware limitations, because of mostly because of the hardware resources, actually. And let's see an example of how explain works. Actually, this explain actually Postgres in Postgres is not using a sequence of the execution plan is not in a sequence of operations. It is actually organized like a tree, like an evaluation tree, because as you can see here in this sequence of operations, relational algebra operations, we have some intermediate results, but this is just for readability. Actually, we can put them all together into a very long operation, by merging the intermediate results. So this one, actually the very long operation is organized like a tree here. And I don't know if you are familiar with abstract syntax tree or not. So have you taken the compiler course? No. And actually the most of the programs could be represented as a tree. So it's kind of similar to how this how it is organized like an abstract syntax tree. So, but this is just from the theoretical part, and let's have a look at how this works in practice. It's been a while since the last time we used one compiler in our lecture. So in this example here, we have two tables. We have a table of authors, and we have a table of books written by the authors. And you can see here we have several things. The first one is we try to explain this query here without the analyze keyword. And the second thing we need to consider here is this one. In this example, we are using a join to implement the query, and in this example, we use a subquery to implement the query, and both of them are using the analyze keyword. So let's see the difference between the three among the three different statements here. So as you can see here, on the left hand, on the right, so this is the result of the first this is the result of the first statement, and as you can see, the Postgres is giving us the query plan organized like a tree. but since we don't have the analyze keyword, it's estimating the cost. It is estimating the cost. It won't give us the actual execution time. However, in the second one, we didn't change the query here. In the second one, we added the analyze keyword, and you can see it prints out 2 more lines of output. The first one is the planned time, which is the estimated time of the execution plan, and the second one is the execution time, which is the actual time used for executing this query. So this is the example here, and the last example is we are using a subquery here to, instead of a join, and to implement the same query. And you can see the execution time is a little bit faster actually than the join here. This means that actually in most of the time joins are faster than subquery, but it's not always, because joins sometimes can give us a very large table. And another thing to consider here is, in this example here, we only insert 3 authors and 6 books. If the table grows much larger, then this join could be faster than the subquery. So actually the performance of the query the performance of a query does not only depend on how it is expressed, it also depends on what kind of the nature of the data it has been applied to. So sometimes some queries are good for larger tables, and some queries works better for smaller tables. So this is what you should consider in practice. And okay, just now we have learned how we do performance tuning. We learned what are the factors affecting the performance of the queries. We learned indexes. We learned how some tricks for speeding up the query execution. And we learned a practical statement that is helpful for us to analyze the performance of queries. And now let's look into some more mechanisms about how DBMS works. So this is so the key concept here we are going to learn is transaction. So the purpose of DBMS is to maintain information in an environment that is shared. So in our practice in this course, you are the only user for your database, but in practice there could be multiple users using the same database. So the information is actually shared among these users, and in this environment it could be unstable because there could be many practical problems when you do the production level of database. There could be hardware failures, there could be software failures that could affect the data you have stored in your database. So we have to. So but this is the environment. This is how it is in practice. But for each user, their work should be unshared. From their point of view, the data should be unshared. So it should not be affected by other users unexpectedly. So that's the first thing. The second thing is, as a user, you are expecting the database to be stable, to be free from all the potential failures. So the ultimate goal is to actually, in one sentence, is to maintain data integrity at all times. And there are three important concepts here for this goal. So the first one is transaction processing. So it is related to the set of techniques for managing logical units of work which may require multiple database operations. So, but we don't worry about the concepts here. So we will look into the keywords later on. And the database system should have proper concurrency controls, as multiple users may access the database at the same time. And the last one is it should have some mechanisms for recovering data. And we will go through the first two topics here in this course. And before we look into how transactions are processed, we need to know the definition of transactions. Actually, a transaction is considered as an atomic unit of work in one application. And although it is considered as atomic, it may require multiple database changes. So to maintain integrity of data, transactions must be ACID. So ACID, here the A stands for atomic. So atomic means, although it could contain multiple changes for a database, atomic here means that this a transaction must be either fully completed or completely rolled back. So it's either success or not taking any effect at all. So this is the definition of atomic. The second one is consistent. So a transaction must be consistent. So if the database system, the state of the entire DB is consistent before the transaction is executed or committed, it should also be stable after the transaction has been applied. So this is consistent. It should also be isolated. So transactions should not interfere each other. And the last one is it should be durable. It should be restorable after system failures. So these are the four characteristics that transactions must be satisfying. So here's an example of a transaction. So let's consider doing a transfer of bank funds. So what can we do is assume we have two tables. We have accounts table, we have branch table, and we are trying to move certain number of dollars from one account to another one. And the first thing is we can maintain the branches as a sum of balances via triggers. So we can use triggers to maintain the data integrity. And the actual transfer from one account to another could be implemented as a function like this. And this entire thing, including the triggers, the action taken by the triggers, the function, is all considered as one transaction here. So transactions are actually a conceptual thing here. So it is made up of several database changes. However, as a whole, they must be atomic. They must be either fully completed or everything must be rolled back. So this is transaction, an example of the transaction here. And here are more concepts about transactions. So a transaction must always terminate. So it should be either successful or unsuccessful. And If it is successful, this is related to the atomic nature of transactions. If it is successful, all the changes will be preserved for this transaction. And if it is unsuccessful, all the database will remain unchanged. So the intermediate step of the transaction, of a failed transaction, will not affect the database. So this is the concept here. And transactions must be consistent. And the consistent means before the transaction and after the transaction. It doesn't have restrictions on the intermediate state during the transaction. For example, in our previous bank transfer example, we are using some triggers to update the balance of branches. And during this transaction execution, actually before we apply the trigger, the system is not consistent because the balance of the branches are not updated yet. So this is allowed. So intermediate states during a transaction could be inconsistent. However, before and after the transaction, the database, the state must be consistent. So that's the consistency here. And now let's, and before we come to the last topic today, let's have a 10 minutes break, and we will have a look at how DBMS perform transaction scheduling and how we calculate the serializability. And you can grab some snacks here. All right, let's start the second half of today's lecture. So just now we learned about the basics of transactions. We know that transaction is made up of a few database changes, but these changes are all collected as a whole transaction that is atomic. And now let's see because different users could provide transactions for the DBMS to execute at the same time. And let's see how the DBMS could schedule the execution of transactions. So here, before we jump into the details, let's simplify the problems here. So because transactions consist of all kinds of database changes, and let's only consider these operations here. So the first operation to be considered here is read, which is to transfer a data item from database to memory, to read from the actual table. This is read. And the second one is called write, which is to transfer the computed result from the memory to the actual database, to the actual table. And the third one is begin, which is the option to start a transaction. The fourth one here is commit, which means that a transaction has been successfully completed. The last operation here is abort, which means that the transaction is failed. And all other operations are ignored here because most of them only takes place in the memory space and they are not affecting other transactions. So that's why we only consider those operations which may affect other transactions. And here are more details about what we will consider here. So let's try to relate the SQL queries to the read and writes we have defined just now. So select is essentially a read operation for database. Select will only read from the database to the memory. And insert is just write. So we are just writing from the memory to the actual table. Update and delete could produce both read and write, because for update we need to read the data into the memory first, and then we modify that data and write it back. For delete, we need to read the information first, and then we remove it from the actual table. So both update and delete would produce both read and write operations. And here, let's assume each operation involves only one tuple here. And let's use these notations here. Let's denote the items as x, y, etc., and operations as read, write, commit, abort. So let's use read, write, RW to represent read and write operations. So this one here means read a tuple x. This one here means read a tuple y. This one means write to tuple x. This one means write to tuple y. So here's the notations we will be using. So notice that here we give names to the items, to the tuples, and items with the same name are in different transactions are shared objects, which means that they are accessible by different users. So for example, for x, this is the first assumption. Another assumption here, and And now, since just now we discussed, we consider 5 types of operations. Now let's further narrow down the operations to consider. We don't explicitly state the begin, commit, or abort. So we will just ignore those three operations related to the lifetime of a transaction. So let's just consider read and write here, and denoted like this. So let's so a transaction schedule is a schedule for executing multiple transactions, and let's try to have a look at this. It's a schedule for executing a transaction made up of individual operations. So let's have a look at an example here. So let's consider the previous bank transfer example. So in this bank transfer example, this transaction is made up of several steps. The first step is to get the balance in the source account. The second one is to get the balance in the destination account. And then we do a check if the source balance is sufficient. Then we update the source by subtracting the transferred amount. And we will also update the destination by adding the transferred amount. As you can see here, in this transaction, the intermediate steps could be inconsistent, but that's not a problem. The consistency is just applied to the restriction of consistency is just applied to the states before and after executing this transaction. So it's fine that the intermediate steps are not consistent. So let's try to use X to denote the source account, and let's use Y to denote the destination account. We can summarize these steps as a read from the source account, a read from the destination account, a write to the source account, a write to the destination account. So this is a summary of the read and write operations for this transaction here. And remember, we mentioned that update and delete actually involves both read and write, but let's simplify the update and delete as writes, because the overall effect is just a write. It's reading from the database and then overwrite that piece of data. So the overall effect is just a write. And deletion is like reading from the database and remove it from the database. So the overall effect after this operation is just a write. So let's simplify update and delete as write here. So let's further simplify the notations. So just now, this one here is the schedule for transaction. So made up of 2 reads and 2 writes. So as we just discussed, databases could have multiple users, and these users could use the database at the same time. So they could provide transactions for the DBMS to deal with at the same time. So when multiple transactions run in parallel, they should be run their own operations in a well-defined order. And sometimes the operations from different schedules, from different transactions, could have interleavings. So for example here, let's assume we have 2 transaction schedules, T1 and T2. So we can either run them in a serialized manner, which means that we run them one by one, or we can run them concurrently, because most of the computer systems are using multi-core CPUs, and in multi-core CPUs, the process or the tasks are conducted concurrently. So different transactions could be executed concurrently. And this one here, as you can see, before finishing all the options of the first transaction, the DBMS could start processing the second transaction. So this is called concurrent execution. So the overall effect of executing a single correct transaction is to map the DB from one consistent state to another consistent state. So similarly, if we just execute sequences of transactions, we are mapping the states, consistent states in a sequence. And the sequential execution of transactions, assume all the transactions are correct, will not give us anomalies. It will always give us consistent states. So, but if there are interleavings among the individual operations of transactions, there could be inconsistencies. So let's have a so as we just mentioned, there are two types of schedules. The first one is to sequentially execute all the transactions, and this is called serial execution or serial schedule. So which means that we execute the transactions one by one. We finish all the operations of one transaction, and then we finish the second. We start to process the second transaction. So this is called serial execution. And like we have discussed, serial execution will guarantee a consistent final state if the initial state is consistent and all the transactions are correct. And in comparison, we have concurrent schedules, which means that the operations could be interleaving, and sometimes the concurrent schedules are okay. For example, for T1 we read from X, we write from X, and then we read from X, and according to the value of X, we write to the value of Y. This is T1. For T2, we just read from X and write to X. This is okay. This is okay. However, this one could cause anomaly, because as you can see here, we read from T1 is reading from X first, and it writes to X afterwards. But the write of X, the write to X of T2 happens after T1 writes to X. So this X value of T1 is overwritten by T2 here. And then when T1 reads it to decide the value of Y, it's actually reading the value of T2. It's reading the value of T2. This will cause anomaly here. So if you have experiences of programming concurrent programs, you will know that, okay, there are actually a lot of inconsistencies when you have interleavings between threads and processes. So this is just an example here. So if the data used by one transaction is overwritten by another transaction, it could cause problems. So here we have two types of concurrent schedules. The first type is that they will give us a stable final state. The second one is they may cause anomalies. And how do we determine if a concurrent schedule will give us anomaly or not? So this leads to the concept of serializability. So serializability means that, so this is the mathematical or more formal definition of serializable schedule. In summary, it is like this. So we want to determine if a concurrent schedule will cause anomaly or not. If it is serializable, it means that it will generate the same result as if we execute the concurrent schedule, as if we execute the transactions in a serial schedule. So it will give us the same final state as if we run the transactions in a sequential manner. So this is the definition of serializability. So if a concurrent schedule is said to be serializable if we can find a serial schedule that could give us the same final state, then it is serializable. So this actually means, so from the definition we can see that we want to find an equivalent serial schedule for this concurrent schedule. So this is this requires the check for schedule equivalence. Like the normal forms, there are different standards for serializability. So here we discuss two common formulations of serializability. The first one is conflict serializability. This will guarantee that the read and write operations occur in the right order. The second one is called will serializability, which means that it will guarantee that the read operations will see the correct version of data. And let's go through them one by one. So conflict serializability. So let's consider two transactions, T1 and T2, working on the data item of X. So here are the possible orders of read and write operations performed by T1 and T2. So this is T1 executed first. This one is T2 executed first. So read from T1 of X and then T2 read X. Is it equivalent to T2 read X first and then T1 read X? So is it semantically equivalent here? Yes, it is actually equivalent because they are even essentially reading the same data because they are not modifying the data at all. So let's see the second example here, the second scenario here. So T1 read X first, and then T2 write X. And then the second case is T2 write X first, and then T1 read X. So are these two equivalent? Will they behave the same? No, right? No, because the write from T2 will affect the order of writing from T2 will affect what is read by T1. So the result of reading X from T1 is affected by the order here of write. And similarly, this one is also not the same. And what about the last one? Are they equivalent? So both of them are writes, but they are in different orders. Are they equivalent? Actually, no. Why? This one is both of them are read, then it's okay. Both of them are write, they are it's inconsistent. It will cause anomaly because it will affect the final state of the overall system. So in this case, the final state is determined by T2. In this case, the final state is determined by T1. So the only safe here, the only safe operation, the pair of operation here is just to read. So as far as it involves write from multiple different transactions, it may incur some, it may cause some problems. So here are the 4 combinations of conflicting pairs of read and write operations. So as far as there's a write, it could end up in problems, end up in conflicts. So the conflicting pairs is an important concept here for conflict serializability. So let's have a look at an example. Let's try to decide if this one is conflict serial. This schedule is conflict serializable. So this is a concurrent schedule. As you can see, we started processing T2 before finishing processing T1. So let's try to transform this concurrent schedule to a serial schedule. So what we can do is we can look for non-conflicting pairs and swap them the execution order. So the first thing here is we look for non-conflicting ones. So the first possible point for doing this swap is here, between write A from T1 and read A from T2. But we can't do the swapping because it's conflicting. If we change the order, the semantic is changed. So we can't do the swapping here. The second possible point for doing this swapping is here. R1 read A and read B. We can safely do the swapping here of the execution order because they are not conflicting. And then let's do the next swap. So write A and write B. Can we do the swap here? Can we swap their execution order here? Yes, because they are writing to different data items. So we can swap the execution order here, We can swap the execution order here. And then there's nothing left for us to swap. And then we go through from the start again. And let's see, can we swap? This one is not meaningful for swapping again because we just swapped from RA first to RB first. So we don't swap it back. So can we do the swap again here to execute WB first and RA after WB? Can we do this? It's okay because they are operating on different data items. So we can do the swap again, and then we can get a serial schedule. We can get a serial schedule in the end. So this means that this concurrent schedule is essentially the same as this serial schedule here. So this means that this concurrent schedule is conflict serializable. So it is safe. But doing the swapping here is not very effective. So we have a better algorithm of doing this, of checking conflict serializability. So let's have a look at this algorithm here. So for checking, in order to check conflict serializability, we need to show that the ordering in the in the concurrent schedule, if the ordering in the concurrent schedule cannot be achieved in any serial schedule. So if this concurrent schedule cannot be converted into any serial schedule, then it is not conflict serializable. It is not safe. So how can we do this? How can we do this checking here? So the method of doing this is to first build a precedence graph. So this graph, this is a graph. It is made up of nodes and edges. So the nodes are the transactions. The edges are the representing the order of action on shared data. So arc from T1 to T2 means that T1 acts on a piece of shared data before T2 on a conflicting pair here. And once we get the graph, if there's a cycle or a loop in this graph, it means that this concurrent schedule is not conflict serializable. So let's have a look at an example here. So in this example, we have 3 different transactions. And this is a concurrent schedule, and we need to decide whether this concurrent schedule is serializable or not. And first, in order to build the graph, we need to determine the nodes and edges. And let's first determine the nodes. So the nodes are pretty simple here. We have 3 different transactions, so we have 3 different nodes. So we have 3 nodes here. And let's determine the edges. So we need, in order to determine the edges, we need to go through the shared data items one by one. So let's go through A first. So for A, T1 raise A, T3 raise A. This is not conflicting. So we don't put, so there's no need to put an edge between T1 and T3, because although T1 is reading A first, T3 acts on A later after T1. We don't put an edge here. We don't put an edge here because it's not conflicting. Let's try to find conflicting pairs. And a fast way of finding conflicting pairs is to look for writes. So let's speed up this finding process. So let's look for write of A. So there's only one occurrence here. So only T1 is writing to A. And we can see that T1 writes to A after T3 reads A. So, there's a typo here. This T3 should read A, and T1 is writing A. Sorry. T3 reads A before T3 reads A before T1 writes to A. So we have an edge for from T3 to T1. So this is for A. This is what we get from A. Let's try to look for conflicting pairs for B. So let's look for writes for B first. In this example here, only T3 is writing B. So let's look for how other transactions works on B. So in this case, T2 reads B before T3 writes to B. So there's an edge from T2 to T3. And let's look for the case of C. So in this case, we have 2 writes for C. So T1 is writing to C, T2 is writing to C. And the T2 writes to C before T1 reads C and T1 writes C. So we should have an edge from T2 to T1. So we have 3 edges here in this graph. And once we get the graph, So what's the next step to do? Do you still remember in our previous slide? Yes, check for cycles. And in this graph, there's no cycle. So the schedule is conflict serializable. This schedule is safe. And let's try to do a small variation here. So can you quickly come up with a change to the order here to make it not conflict serializable? Actually, let me give you the answer. So actually, if we change the order of read C and write C here between T1 and T2, there will be a loop. If the read C from T1 happens before the write C of T2, and this write C of T2 happens before the write C of T1, it will give us a loop. So T1, there's an edge pointing from T1 to T2. There's an edge pointing from T2 to T1. So there's a loop. So in this case, if we just swap the sequence of RC and WC here, it will become not safe, not conflict serializable. So this is how we calculate conflict serializability. And the second formulation of serializability here is view serializability. So view serializability is less conservative than conflict serializability. So it is less strict. So therefore some safe schedules that are view serializable are not conflict serializable, but all schedules that are conflict serializable are also view serializable. And the same as with conflict serializability, it is also based on the notion of schedule equivalence. So we are trying to find an equivalent serial schedule for this concurrent schedule in order to verify the serializability here. So the idea here is the overall idea of view serializability is to guarantee that if across two schedules they read the same version of a shared object and they write the same final version of an object, and then they could be viewed as equivalent. So two schedules are view equivalent if and only if they raise the same initial value, and then they write the same. They perform the same final write, and in between the initial value, the read of the initial value, and the final write, they follow the same order of reads and writes. They follow the same order of reads, and don't get overwhelmed by these symbols here. And there's a summary. So in short, for all shared data items, the initial reader should be the same. The initial reader transaction should be the same. The read and write sequences should be the same. And the final writers should be the same. So in order to check view serializability of a schedule, we need to find a serial schedule that is view equivalent to the initial concurrent schedule from all the possible serial schedules. And the number of possible serial schedules is is n factorial. So n is the number of transactions involved in the schedules. So n factorial is actually all the combinations or all the permutations for different combinations of orders of sequences of transactions. So if we have two transactions in a serial, in this case, we will have 2 factorial, which is 2 possible serial schedules. If we have 3, then it is 3 factorial, which is 6. And if we have 4, then it is 24, and so on. So this is real serializability. And let's have a look at an example of how do we check real serializabilities. So the first, this is an example here. As you can see, we have 2 shared objects here. The first one is A, the second one is B. And the 2 schedules, this schedule is a concurrent schedule because we started to process T2 before finishing the processing of T1. So the first step of doing this is to find out all the n factorial serial schedules here. So in this case, n is 2, and we only have 2 possible options. Oops, I messed up the animation. But anyway, let's start. And so these are the 2 serial schedules possible for T1 and T2. And if we have 3, assume we have 3 transactions, how many possibilities do we have? 6, right? 6. So let's go through, let's see if one of them is serial, is real equivalent to the original concurrent schedule. And how do we check that is, remember there are 3 things we need to check. The initial reader, the final writer, and the read and write sequences in between. So in the concurrent schedule, T1 reads for A, let's go through this check for every shared data item. So for A, in this concurrent schedule, T1 performs the initial read, and T2 performs the final write. And T2 is reading from the write of T1. This is for A in this concurrent schedule. And for B, T1 is doing the initial read, T2 is doing the final write, and T2 is reading the write result of T1. So this is in the concurrent schedule. And in the serial schedule here, T1 in this first example here, T1 is reading for A, T1 is doing the initial read, T2 is doing the final write. T2 is reading the write result of T1. This is A. For B, T1 is doing the initial read, T2 is doing the final write, and T2 is reading from T1 as well. So essentially they are the same. So the concurrent schedule is real equivalent to this serial schedule here. So that's why this concurrent schedule is real serializable, and it is safe. It is safe. So this is how we calculate real serializability. And that's all for today's lecture. I will create additional examples, maybe some more complex examples here for you to practice with. So keep updated. And there's no physical lecture on next Monday, but I will upload a video to go through all we have learned for this course. So basically we are learning as a database programmer, and we learn how to design databases, how to design data models, and we learned how to use SQL, which is still one of the most popular programming languages. And we also learned some theoretical theories about DBMS, And these series are actually used for DBMS to operate. And why we learn this is because we can use, if we know the mechanism of DBMS, we can do performance optimization. We can know how it works to avoid anomalies. So that's the overall structure of this course. And I will give you a video of summary for this course later next week. So that's all, and thank you for coming to this lecture. Actually, next week, the entire week, I will not be here in Sydney. But there will be a guest lecture on Thursday. I hope you have seen the notification. So the guest lecture is from Dr. Jin. He's from a local company here. And if you are interested in looking for internships or perhaps jobs related to databases, you can contact him in the next guest lecture on Thursday.